Right. In case of aldehydes and ketones, so first you need to learn all the important common names. Acrolein, cinnamaldehyde, crotonaldehyde, what is vanillin, furfural, pivalaldehyde, mesitylene, mesetyl oxide, and phoron. These are the most common ones which you will keep coming across. So you better learn that part. Next is about the preparation of aldehydes and ketones from various functional groups. Alkanes does not give directly any aldehydes and ketones, but when it comes to alkenes, you can do ozonolysis. So all you need to do is a reductive ozonolysis, break the double bond, convert them into respective aldehydes or ketones. This we have done in alkenes. I'm sure आपको पता है क्या करना है, right? Next is about Wacker process. Wacker process is using on the same alkenes, if at all we use air or a moist air in the presence of palladium chloride. Okay, palladium chloride is a base on which alkenes are adsorbed, then moist air has been sent to react with some heat. So that will make this alkene into an aldehyde form. Okay, basically it would be like, addition of H2O only. So you can imagine as if like there is sorry, addition of this OH group here. So instead of this H, imagine OH has been added. So that will convert into an enol form, which will eventually become a aldehyde or a ketone form. Okay. If the unsymmetrical double bond is present, wherein one side we have two hydrogens, the other side we have one hydrogen, that means it will form a ketone. Okay.
सर तो OH वाला मिडल वाले कार्बन पे हो जाएगा.
Yes, middle wale carbon pe aa jayega. So
Yes.
that's how we can get an aldehyde or a keto form. This is Wacker process. Oxo process is you use carbon monoxide and H2 in the presence of cobalt carbonyl salts complexes. Then you could imagine as if you are making a electrophilic addition following Markovnikov's rule, wherein we make this pi bond to attack on this electrophile first. Positive charge will come here and H minus will come here. So you always think in that way. It is easy to understand. That is not exactly how the mechanism happens, but this is an easy way to understand that pi can be attacked here and H minus is attacking here, and that's how you will end up getting an aldehyde. Clear with Wackeran process, oxo process.
Yes, sir.
Next is alkynes. Alkynes, this is the most important reaction, Kuchro's reaction. Basically, alkynes are subject to the mercuric salts, wherein a mercury will form a mercuric bridge, and then water will attack on a carbon which is relatively more substituted. Here it is symmetrical, but otherwise if it is more substituted, that's where you push the water and break the mercuric bond here. So then you will get an OH group here with a double bond, and mercury would come out giving away negative charge on carbon, and that negative charge will take H plus from the dilute H2SO4 which is present in the solution and converts into enol. That enol converts into keto form. In this case, it is aldehyde. Like if it is unsaturated alkyne in here, it will convert into keto form. Okay.
Yes, sir.
Next, hydroboration oxidation. Instead of directly using B2H6, see B2H6 problem is B2H6 can also reduce aldehydes further into alcohol. So we do not want that. So instead of using B2H6, the alternative reagent is SiA2BH, that is secondary isoamyl boron hydride. Okay, secondary isoamyl. Amyl means 5 carbons. Okay, like this 5 carbon at a secondary position connected with boron. Got it? So like this with boron. So this way with a hydrogen. So this is called SiA2BH. When you use that, because of its bulky nature and having only one hydrogen, this hydrogen will be slowly added onto this part of the carbon, and this part of the carbon gets associated with boron. And once the attachment happens, immediately you do oxidation by using peroxide. So this bond will go away and OH will come, which will convert into an aldehyde form. Okay. दिस इज हाइड्रोबोरेशन ऑक्सीडेशन.
सर H2O2 के बाद क्या हो रहा है सर?
H2O2 इस ग्रुप को निकाल के OH लेकर आ जाएगा. ये इनॉल बन रहा है, इनॉल टॉटोमराइज होकर आल्डिहाइड में कन्वर्ट हो रहा है. ओके.
ओके सर.
दिस इज वेरी सिमिलर टू हाइड्रोबोरेशन ऑक्सीडेशन. क्लियर?
यस
राइट.
सर.
Next is cold dilute KMnO4, which is Bayer's reagent, and we know that Bayer's reagent will actually create hydroxyl groups, two hydroxyl groups. So one OH here and one OH here, and after adding there is still a double bond left, and one of the part can be read as enol, and that will tautomerize into keto form. The other OH will remain. Okay. In fact, if you have a secondary alcohol, the secondary alcohol will also get again oxidized in the presence of Bayer's reagent to convert into keto form. Okay. But this form of oxidation is weaker. So we use here not Bayer's reagent exactly. We use again KMnO4, alkaline KMnO4, but not with this critical conditions of 1%. You remember the condition, right? It is not like 1% cold dilute, not that. Normal KMnO4 if you use, that can oxidize the second degree alcohol into ketone. Okay.
यस सर.
So we can further oxidize that to convert into keto form. Next, you could perform ozonolysis to get the same product. Reductive ozonolysis will always help in removing out, these two pi bonds, but the sigma bond will remain, convert that into keto form. Okay. So any problem with the preparation from alkynes?
नो सर.
Next is preparation of aldehydes, specifically aromatic based. So if I have to compare, if at all have to convert benzene form into an benzaldehyde, then there are two main reactions. One is Gattermann reaction, the other one is Gattermann-Koch reaction. In Gattermann reaction, we'll be using HCN in the presence of dry HCl added with anhydrous AlCl3 or anhydrous zinc chloride. Most of the time, it is zinc chloride that is used more than AlCl3. So what happens is that the lone pair present on nitrogen will first take H plus from the dry HCl, and then it creates a sense of positive charge here. Now you might ask, sir, how did we get dry HCl? So basically for that only we are using this Lewis acids, because this HCl is dry, which means it is in the form of an ether or it is highly concentrated. So this breaking of HCl becomes difficult unless you add it to water. The other way is you add a Lewis acid like AlCl3 or ZnCl2. So chlorine will get associated with any of these two and releases H plus into the solution. And that's when the lone pair from nitrogen will take away, and that creates a positive charge on carbon. And positive charge on the carbon makes it an electrophile. So benzene is ready to make an electrophilic aromatic substitution. That leads to the formation of an aromatic imine, okay, or an aryl imine. A C double bond NH bond is called as an imine bond. Imines are highly unstable in aqueous solution. Once you are prepared the imine form, add water. This will break to convert into an aldehyde form. Okay, just a second. See, you have a work. No, it is over. Sorry. So imines on hydrolysis will convert into an benzaldehyde.
सर HCl अपने आप से क्यों नहीं ब्रेक हो रहा था? ल्यूइस एसिड क्यों डालना पड़ा?
क्योंकि हमने ड्राई कंडीशन में रखा है, मतलब वाटर में नहीं डाला है हमने. वाटर क्या करता है, हाइड्रेट करके दोनों को सेपरेट कर देता
सर तो वाटर क्यों नहीं डाल देते?
है। ओके,
सर वाटर डाल के भी हो सकता है क्या? यूएस एसिड नहीं
क्या
डाला,
बेटा,
वाटर डाला तो?
वाटर डालेंगे तो HCN भी टूट जाएगा H प्लस और CN माइनस की तरह। ओके,
हाँ,
एक्व
ठीक है सर।
सॉल्यूशन में हमें वो नहीं चाहिए ना, हमको चाहिए कार्बन के ऊपर पॉजिटिव चार्ज लाना। हम्म,
यस सर।
ठीक है। और HCN कभी इलेक्ट्रोफाइल की तरह बिहेव नहीं करता एक्व सॉल्यूशन में, क्योंकि H प्लस ऑलरेडी प्रेजेंट है, इजंट इट क्लियर?
यस सर।
सो उसको अगर इलेक्ट्रोफाइल की तरह बिहेव करवाना है तो हमको ड्राई कंडीशन में लेके जाना पड़ेगा। क्लियर है बेटा? And
हाँ सर।
imines are usually unstable. On hydrolysis, they'll give away ammonia and aldehydes. Okay. Next, Gatterman-Koch is while using carbon monoxide and HCl, same logic with a dry HCl with AlCl3 or CuCl. Okay. Here also, this would be acting with a Lewis acid, releasing H plus. The negative part on the carbon will attack on the H plus, converts into this HC triple bond O plus, which will eventually observe like an electrophile. So benzene will attack, electrophilic substitution will take place and converts into benzaldehyde directly. Okay. So remember, these two are a very good source of making an aldehyde group on benzene. Clear?
यस। हाँ
Right. Next, this is an important part of the topic because all the reactions what we learned so far, they have been already repeated once in a while. If you take toluene and react with chromyl chloride in CS2, okay, chromyl chloride is CrO2Cl2. CrO2Cl2 typically have a structure like this that after hydrolysis converts into an benzaldehyde, which is called as etard reaction. Okay, basically what happens between these two hydrogens here on a toluene, these two hydrogens which are hyperconjugating with the benzene ring, they would have bonds strongly associated with oxygen here, correct? So you could imagine this way, from the oxygens which are present here, they will insert onto this carbon and O will come on to the other part of the oxygen, right? So this way you will see one oxygen will take H, the other oxygen will make a connection with carbon. Don't worry about sir ये कैसे टूटेगा क्या हो रहा है, that is not our dynamics to understand. Okay, so you just notice that these two bonds are broken, which will get associated with two parts of the chromyl chloride, right? And once this is done, now the bond breaking will start. So from here it will start to become double bond, this will start pushing here, so you will get one part here, and this will be also ending up at as a double bond here, you will get another part here. Got it? And this will again react with the next molecule, and this will keep on happening till it becomes CrOH thrice eventually. Got it? So every time you see, now this time again this double bond will push, chlorine will come out. Okay, so Cl will take away H plus and come out, and this will be ready for the attack on the next molecule. So this would keep on happening till you will get everything sorted as CrOH thrice. Clear beta?
सर, पर फर्स्ट टाइम में CrO2Cl2 अटैच क्यों हो रहा है सी पे?
First time is CrO2Cl2 attached.
CrO2 हाँ हाँ।
See, between these two, between carbon and hydrogen, the bond is weaker because of the hyperconjugation. है ना, नो बॉन्ड है ना इसके ऊपर, H प्लस है इधर, ये डबल बॉन्ड है इधर, करेक्ट?
हाँ सर।
बेंजीन के साथ इस तरीके से, दिस इज द हाइपरकॉन्जुगेटेड स्ट्रक्चर, बराबर, correct? Now what happens, oxygen which is having a double bond with chromium here, with double bond here, chlorine and chlorine here, right? So this pi bond of carbon which is having H and another H plus here, this pi bond of carbon will try to attack on oxygen and electrons will be pushed towards chromium. because chromium is at a very high oxidation state, na beta. So it will have high electronegativity on it. Got it?
Yes, sir.
So this is the push, and as it goes away, ये ऑक्सीजन O माइनस बन सकता है, which will consume this H plus. ठीक है?
हाँ सर.
That's how the insertion takes place. आप बोल सकते हो सर 3 मोल्स में क्यों नहीं हो रहा है? देखो 2 मोल में ही बहुत बल्की हो जाएगा ये. उसके बाद वो हैंडल नहीं कर पाएगा, ब्रेक कर जाएगा. Okay? So that's why it is not noticed that all the 3 hydrogens are involved in making this complex. After 2 moles, it will start breaking, and that will eventually convert into an aldehyde form. Okay?
Yes, sir.
The same logic, just like how we did it for chromyl chloride, the same thing works with CrO3 also. Okay? Chromium trioxide also. Chromium trioxide is a red color liquid. You take it in an anhydride form, and this will also give you a similar type of complex here. Thereafter, on hydrolysis, it will convert into aldehyde, and chromium will convert into this green color solution. Clear? I mean green PPT here.
हाँ सर.
Next, see in NCRT, one thing it was given, Cl2 in H nu, the equivalents were not mentioned. Correct? Equivalents mention nahi kiya gaya. But he meant to take 2 equivalents only. Otherwise, ये 3 equivalents भी जा सकते हैं. There wasn't any issue of removing out this hydrogen also. Imagine if you thoroughly provide 2 equivalents of chlorine. So 2 hydrogens will be substituted by chlorides. And thereafter, if you do substitution of aqueous NaOH, right? This would make the Cl minus to go and OH minus to take place. And 2 OH minus will convert into an aldehyde form. Got it?
Yes,
This
sir.
is another easy way to prepare. Next, we know that how to convert benzene into ketonic form. That is via acylation. So you take any acyl chloride, react in the presence of Lewis acid like AlCl3, or you can take anhydride in the presence of AlCl3. Both will convert that into an acyl form. Clear?
हाँ सर.
We can also take acid in the presence of HF or PPA. PPA is polyphosphoric acids. They would also help to remove this water out and make this acyl group to connect on benzene. That's how we can get an ketonic form here. Now, these are all about aromatic forms of aldehydes and ketones. Next is general alkyl halides. How will they convert into aldehydes and ketones? If you have a 1-degree alkyl halide, use DMSO. By using DMSO, we can convert that into an aldehyde form. Okay. So basically, first a chlorine will go and connect on sulfur. This is the structure of DMSO, that is CH3, CH3, S double bond O. Oxygen's lone pair will connect here. Chlorine will come out here. So chlorine will get connected here first, correct? And once the oxygen gets connected here, oxygen will try to push it into a double bond form, and that's where the uh, uh, group like this we will have S. Sorry, allow something as simple as S with, imagine like O getting connected to CH2 here with R here, and let me put this as hydride here with the chloride in this case. Okay, one more methyl group is there. So this is the kind of bond we are expecting it to form first, and this bond has to be pushed here like this, so that the sulfur can take away its electrons back here. So that way, this will convert into a double bond form, and this H plus which is released will again collect out with chloride. So we will get this as double bond CH and R plus methyl sulfur, and methyl will remain, plus HCl will come out. Got it? This is typically how it happens when it comes to DMSO. It will convert into an aldehyde, releasing out this HCl vapors.
Sir, Cl
If
attack on sulfur is electrophile nucleophile.
Sulfur is trying to retain its electrons, so it is an oxidizing agent. So it is breaking the bond with oxygen, as this carbon will try to support a pi bond with oxygen. By that, as the electrons come onto sulfur, chlorine would be out, and that makes it as a dimethyl ether. Okay, thioether. And this
Sir,
Cl minus which is coming out can take this HCl, H plus. Okay. Hmm.
सर वो नहीं पूछ रहा था सर. Cl attack on sulfur initially. Electrophile nucleophile, no?
This is a nucleophile part. This is a nucleophile attacking here. So nucleophilic
Okay.
addition. Hmm? Hmm. Next, if you have two chlorines, it becomes even more easier. Okay. So with DMSO, you can be like bargaining two chlorines out with one oxygen to get combined. So whether you have a single chloride or a dichloride, they will end up getting into aldehydes and keto forms. And directly conversion of alkyl halides, this is the only method which we can use. Okay.
सर दो क्लोरीन में कैसे होता है?
दो क्लोरीन में आप ऐसे समझो कि दो मॉलिक्यूल्स को कनेक्ट हो रहा है, एक क्लोरीन इधर से निकला, करेक्ट, दो मॉलिक्यूल के साथ हो रहा है, यहाँ पे एक डीएमएसओ एक एक क्लोराइड को ले रहा है, दूसरा डीएमएसओ दूसरे क्लोराइड को ले रहा है. ओके.
अच्छा, ओके, अंडरस्टूड.
Next, from alcohols, if you want to convert into aldehydes, we have very specific reagents. Okay. Reagents like CrO3, PCC, PDC, copper and heat, ऐसे बहुत सारे reagents हैं. If this is specifically used to convert them into aldehydes, in fact, there are reagents which cannot be controlled and stopped at aldehydes, like alkaline KMNO4, K2Cr2O7, CrO3 acetone with dilute H2SO4. That becomes Jones reagent. This is called Jones reagent, which cannot control at aldehyde. It has to go all the way up to acids. Okay. So first, let us understand the reactions, and then I can, explain you what is the factor that is making it to control. Check. If you have an alcohol like 2 degree or 1 degree, you use uh, Jones reagent, for example. In Jones reagent, you'll end up secondary alcohol will end up converting into ketones. Primary alcohol will end up converting into an acid. Okay. Here, but when it is in a allylic or a benzylic position, see allylic or a benzylic position, in that case, even the Jones reagent cannot be able to convert aldehydes into acids easily. So ये भी aldehydes के पास रुक जाएंगे. Acids बन सकते हैं, but it takes a very long time. So you can easily extract out the aldehydes present here itself. Okay, this is the challenge that faces in aldehydes and um, benzylic aldehydes and allylic alcohols and benzylic alcohols. Okay, simple alcohols, they all will convert into acids. There is no problem there. Clear? Now, why this happens, what exactly is the challenge, we will see it for, okay, once we go through the reactions. Okay.
यस सर.
Next, second one is scan reactions. Scan reaction is steric ammonium nitrate test, which we have done it in alcohols already. Okay. In alcohols, we have already seen all of these reactions as a oxidation reactions, if you recall. Correct. What is the role of copper and heat? What is the role of MnO2? What is the role of Jones reagent? What is the role of PCC, PDC? ये सब हमने alcohols में कर लिया है. Correct.
हाँ सर.
So that's why I haven't written all of that back here. So there is a complete table that was written in alcohols topic, so you can go through it once. In can test, you will see 1 degree alcohol will convert into aldehyde, 2 degree will convert into ketone, 3 degree will also make a reaction, but into a salt kind of a form. Okay, it will exist as a salt kind of a form, but the reaction will happen. So like here 1 degree is there. This is steric ammonium nitrate, yellow color. It will first convert into red color, and after some time it will start becoming colorless. Okay, and this part of that group which was connected will slowly convert into aldehyde. The same thing will happen even with the second degree, third degree. Third degree, it will become red color and further uh, colorless is not formed. So here color will remain as red. Here it will become red to colorless. Here also it will become red to colorless. Got it?
हाँ सर.
Right. Next is X2 and KOH. That means chlorine in KOH or bromine in KOH or iodine in KOH.
तो ऊपर
So
थ्री
1
डिग्री
degree
कैसा होगा
alcohol if
फिर?
you have. Yes, tell me.
फिर ऊपर रेड टू कलरलेस ऐसा हो रहा है ना?
इसमें
तो
भी
सर,
रेड टू कलरलेस हो रहा है, इसमें भी रेड टू कलरलेस हो रहा है, बट टाइमिंग का फर्क है, इधर थोड़ा जल्दी होगा, इधर थोड़ा लेट होगा।
और सर 3 डिग्री OH में.
इसमें रेडी रहेगा।
ओके.
देखो ये जेई में आ चुका है, मेंस में भी 2 बार आ चुका है क्वेश्चन कि विच ऑफ द फॉलोइंग विल गिव रिएक्शंस विद कैन और विच ऑफ द फॉलोइंग विल गिव कलर चेंज विद कैन। ठीक है, आंसर इज ऑल ऑफ देम। समझ रहे हो? 1 डिग्री, 2 डिग्री, 3 डिग्री, ऑल ऑफ देम आर चेंजिंग कलर्स। क्लियर? एंड ऑल ऑफ देम आर मेकिंग रिएक्शंस। बट अगर यही क्वेश्चन इफ इट वाज framed for something like PCC or PDC, we can say 1 degree, 2 degree are reacting, 3 degree react ही नहीं कर रहा है। ओके,
सर वन
सो
डिग्री
दैट्स अ
OH
डिफरेंस।
फास्ट हो रहा है तो रिएक्शन मैकेनिज्म कौन सा होगा सर?
किसमें?
हाँ इसमें.
जो फास्ट हो रहा है वो 1 डिग्री है, जो
हाँ
थोड़ा
सर,
मॉडरेट हो
रिएक्शन
रहा है वो 2 डिग्री।
मैकेनिज्म.
हाँ हाँ।
तो रिएक्शन मैकेनिज्म कौन सा वाला होगा इसमें?
इसमें देखो यहाँ पर सब्स्टिट्यूशन हो रहा है। पहले ये ऑक्सीजन का ग्रुप सब्स्टिट्यूट कर रहा है सीरियम पे, बट ये इतना इजी सब्स्टिट्यूशन नहीं है। उसके बाद एक इलेक्ट्रॉन निकल जाता है यहाँ से, बिकॉज ये NO2 बन जाता है। दिस विल सॉरी NO3 माइनस जो आ रहा है ना, उसके साथ में एक इलेक्ट्रॉन निकल जाता है यहाँ पर। गॉट इट?
हाँ सर.
और वो इलेक्ट्रॉन के वजह से ही ये सीरियम रेड्यूस हो जाता है Cr+3 में, क्योंकि वो एक्चुअली +4 में था। हम्म।
हम्म.
तो वो रेडिकल रिएक्शन हो रहा है वहां पर। करेक्ट? सो पहले
ओके
सब्स्टिट्यूशन हो रहा है, फिर रेडिकल रिएक्शन हो रहा है।
सर. SN1
फिर
ना?
क्या बेटा?
SN1 हो रहा है ना?
फर्स्ट वाला जो हो रहा है वो SN2 हो रहा है, SN1 नहीं, NO2 निकल रहा है।
सॉरी मैं, हाँ समझा.
ओके। ठीक है, नेक्स्ट। Chlorine in KOH, bromine in KOH, or iodine in KOH, in all of these cases, if it is 1 degree alcohol, something of this kind, you will end up getting an aldehyde. Okay. But if you have a 2 degree alcohol with a methyl group on it, फिर वो आइडोफॉर्म में चला जाएगा और हैलोफॉर्म चला जाएगा। You know हैलोफॉर्म reaction, right? So first this will convert into a keto form, and that ketone will further get oxidized in the presence of bromine, chlorine, or iodine to convert into an acid, and haloform will be formed. Okay, it's not a precipitate. Clear?
यस सर.
Next, Swan's oxidation. This one will also give you 1 degree to aldehyde, 2 degree to ketone, 3 degree no reaction. There are 3 reagents that is to be clubbed and used here. One is DMSO, the other one is oxalyl chloride. This is called oxalyl chloride. This is oxalyl chloride. Basically, it is oxalic acid with chlorides. Okay. Then you have to use a 3 degree amine. So combining these three, no mechanism required here. Directly remember, 1 degree alcohol will convert into aldehyde, 2 degree will convert into ketone. This is same as DMSO on alkyl halide beta. Just like alkyl halide का reaction हुआ है, on a similar case here you will have an aldehyde form. Hmm?
यस सर.
Next is Oppenhier's oxidation, which is the reverse of MPV reduction. In MPV reduction, we were converting a ketone into alcohol. Now what we are doing, we are taking an alcohol and converting into a ketone. Okay. So this is a primary group. Clear? So you see this is keto 1 and okay, 1 second. Check. So this is keto 1 and this is keto 2. Okay. Usually, if you want to convert this alcohol form into this keto form here, right? This is Oppenhier's oxidation. And in Oppenhier's oxidation, what do we usually need to notice is that this keto form which you are taking, for example, here the keto was acetone, and this is a ketone which is forming, right? But more than acetone, you better take something of this kind, okay, like this. Why? See, you need to make sure that, the boiling point of this ketone, you know, this ketone is more than the boiling point of this ketone. Why? Because the reaction as it happens, you need to start evaporating quickly, otherwise the backward reaction will keep happening. So the first, whenever you're taking these type of reactions which are reversible, make sure that the product is more easily evaporating. So in that case, you can notice that keto 1 boiling point should be greater than keto 2. So then the reaction will be driving more in this direction, towards the oxidation direction. अगर उल्टा होता तो backward direction ज्यादा favor करता. Got it? And that is called as MPV reduction. Hmm?
सर पर वैसा ग्रुप बड़ा होने से बॉइलिंग पॉइंट बढ़ जाता है।
बढ़ जाएगा ना बेटा. अभी देखो ये वाला ग्रुप जो है, इसका जो कीटोन बन रहा है, मैं अज्यूमिंग दैट फैक्ट कि ये वाला और ये वाला कंपेयर करूंगा, तो मेरा ये वाला कीटोन ज्यादा बॉइलिंग पॉइंट होल्ड करता है.
सर वो आर और आर डैश और बड़ा भी हो सकता है ना?
उन दैट केस इसको और बढ़ा लेना पड़ेगा.
अच्छा, ओके सर।
ठीक है. हाँ, इट ऑल
हाँ
डिपेंड्स अपॉन हाउ यू आर पुशिंग इट. ओके.
सर, और आइडियली हमने अगर कीटो वन को ब्रांच नहीं किया तो और ज्यादा बढ़ेगा ना बॉइलिंग पॉइंट?
करेक्ट करेक्ट.
ओके
स्ट्रेट
सर।
करोगे तो और बढ़ जाएगा.
हाँ।
हम्म. मैंने जस्ट एज एन एग्जाम्पल की तरह लिखा है उधर. You can take it in any case, but just keep this in mind. This one you have to keep in mind.
यस सर।
Next, with MnO2 and heat, allylic oxidation will take place. That means at an allylic position, if there is an alcohol, it will convert into a keto form or an aldehyde form. So same logic applies to benzyl position also. At a benzyl position, if you have an OH, it will convert into a keto form. A regular alcohols at 1 degree, 2 degree does not make any reaction with MnO2. So it's a very specific reagent only targeting allylic and benzylic alcohols. Okay,
यस सर।
right. The next reaction of aldehyde is from Stephen's reduction. Stephen's reduction is making the cyanides to convert into aldehydes. So what? How do we? How can we do that? You can tin chloride in concentrated HCl. So when you take it in concentrated HCl, it will become SnCl4, releases two nascent hydrogens. These two nascent hydrogens make an addition on this triple bond, convert into a double bond. And double bond is nothing but an imine form. And this imine form with SnCl2 and furthermore two more HCls convert into this complex form first. And this complex on hydrolysis, once the complex is formed, now you make a hydrolysis. It will convert this into aldehyde. This part will break, convert into ammonia, and this will get separated out. Okay. So you will have basically this ammonia is the one which will finally form into NH4 twice and SnCl6 this way. This is the final complex which it is going to form. Got it?
हाँ सर।
Next, dibal H. Dibal H is particularly used to convert any carboxylic derivatives into aldehydes, mainly acid chlorides, ester, and cyanides. And these, when you react with dibal H, see, normally the temperature always need to be in a controlled form here. So it should be around minus 78 degrees centigrade. Then it will convert into an aldehyde form. Okay. If it is at a room temperature, this can further get reduced. I mean, the aldehydes can be further reacted with dibal H and convert into an alcohol part. But this I told you, as per JE, dibal H is not used for this preparation. It is only for aldehydes. Okay.
यस सर।
So dibal H minus will attack here. O minus will form via SNTD mechanism. O minus will again close it, remove the leaving group, and convert into an aldehyde form part. Okay. Next is with Grignard's reagent. Cyanides, when you react with Grignard's reagent, first it will form an adduct like this. Now the carbon does not have any sufficient positive charge for the next molecule of RMGX to attack. So no matter how much excess you take, even if you take excess amount here, the reaction will not take place. So only it will stop at this adduct form, and then hydrolysis would happen. Sorry, in hydrolysis, the nitrogen will take H plus first, and then after that, the bond breaking will take place and convert this into keto form. Okay, this is via Grignard's reagent. Yeah. Next, if you notice for carboxylic acids, from dry distillation of calcium salts, so you can see if you have this calcium salts here, let's say this is an acid with a calcium salt here. On dry distillation, best method to think is like you try to remove out calcium carbonate. You can see this is CaCO3. So calcium carbonate is being removed. This becomes C minus. That C minus is the one which will attach the C double bond O, and this oxygen will take away H plus from here. So that's how you will get a enol form, and that enol will convert into a keto form. Okay. So I guess this part is clear.
Yes, sir.
Right. And this can be done for any kind of um carboxylic salts, I mean calcium salts. On heating, you can see this entire part will convert into a keto form and CaCO3. Now, in case if you have multiple or different types of calcium salts, one, this can itself make a self dry distillation. This can make a self dry distillation, and then we can have a cross distillation also. Okay, so that means from here you can remove CaCO3, and from here the carbon can connect, or vice versa. Here you can remove CaCO3 and this CH3 can connect. Hmm? Now, if you have a formic acid, I mean, if
सर
you
वो
have
एक
a
बार
format,
रिपीट हो गया
हाँ देखो,
एग्जाम्पल 2 वाला.
yeah, let me show you. Suppose if you have CH3, CH2, C double bond O, and CH3 and C double bond O. Here we have oxygen, oxygen with a calcium 2 plus. Okay. Now let us put these three scenarios here. I mean, sorry, in the first, in this scenario here, I would have to remove the calcium carbonate from here. So like this, I have removed calcium carbonate, CaOCO2, correct?
हाँ.
So this is the calcium carbonate which has been removed. So on removing, what would happen? See, CH3, CH2 minus will be stored here, and CH3, C double bond O plus will be present on carbon. So these two are the ones which are connecting to convert into CH3, CH2, C double bond O, CH3. इस तरह से बन रहा है. ओके, ये क्रॉस वाला हो गया ना बेटा. ऐसे स्ट्रेट करोगे तो ये दोनों आपस में जुड़ जाएंगे तो ये बनेगा, ये आपस में जुड़ जाएंगे तो ये बनेगा. ये क्रॉस वाला है. ओके.
हाँ सर वो मैकेनिज्म आप बता रहे थे उसमें आपने बोला कि इनॉल बनेगा और फिर सर पर इनॉल में OH तो दिख रहा है पर डबल बॉन्ड की तरह.
बेसिकली यहाँ पे जैसे बन रहा होता है, ये CO2 बन रहा है, तो जैसे CO2 बन रहा है तो ये CH2 माइनस आ जाता है. ओके.
हाँ
ये माइनस जाके यहाँ पर ऑक्सीजन पे अटैक करता है. करेक्ट.
कार्बन पे. हाँ.
क्लियर. सॉरी, कार्बन पे अटैक करता है. तो कार्बन पे अटैक करते ही एडिशन हो जाएगा, ये O माइनस बनेगा.
यस.
राइट. तो ये जो O माइनस बनेगा, वो क्या कर सकता है, यहाँ से H प्लस लेकर, करेक्ट, फिर से नेगेटिव चार्ज बना देगा यहाँ पर. जो नेगेटिव चार्ज है इसके साथ डबल बॉन्ड बना देगा कार्बन के साथ.
अच्छा ओके अंडरस्टूड.
हम्म फिर वो इनॉल में कन्वर्ट हो जाएगा. आप उसको नहीं लिखोगे तो चलेगा, ये कोई मैकेनिज्म आपको ऐसा पूछने वाला नहीं है. ओके. सो आप
हाँ
बिल्कुल सिंपल तरीके से इसे याद कर लेना, बहुत इजी है. हम्म,
यस
ठीक
सर
है.
समझा.
ना देखो, if you have a formate salt, right, कैल्शियम फॉर्मेट सॉल्ट, तो फॉर्मेट का क्या होना चाहिए, दो फॉर्मेट अगर मिलेंगे तो H2 बनना चाहिए ना. ओके, क्योंकि और कुछ है नहीं उसके पास. H माइनस है और H प्लस है. दोनों मिलके H2 बनना चाहिए। तो देर इज ऑलवेज सम अमाउंट ऑफ H2 विच इज फॉर्म। ठीक है, क्लियर?
हाँ
व्हाट डज दैट मीन? देखो ऐसे कह रहा हूं मैं, एच सी डबल बॉन्ड ओ एंड आई हैव O minus, H C double bond O here, like this. This is with minus and calcium 2 plus. So इसको अभी हम लोग ऐसे निकाल देंगे, कैल्शियम कार्बोनेट को निकाल दिया यहाँ से। तो ये क्या बना? H माइनस बना। दैट H माइनस विल कनेक्ट ऑन टू दिस C, राइट? सो हमको क्या मिलना चाहिए? आल्डिहाइड, सॉरी, not H2, my mistake. It's not H2, I meant to say this one, okay? But this is a poor yield, poor yield बनेगा। Why poor yield? रीजन बीइंग H माइनस लाना बहुत डिफिकल्ट होता है, करेक्ट? H minus is a very I mean it's very difficult to get this H minus part, so क्रॉस रिएक्शन ज्यादा होंगे इसमें। अच्छा, आप बोलोगे सर ये नहीं है तो क्या? इन दैट केस यू स्टिल राइट डाउन दिस, एल्डिहाइड बन सकता है। ओके,
सर
क्लियर बेटा?
LiLH4 माइनस में सर उधर तो H माइनस निकाल के हम कर रहे थे ना।
LiLH4 में
हाँ सर उधर।
H माइनस सेपरेट नहीं किया था बेटा, अलग नहीं किया था अपने। ओके,
हाँ सर।
that was connecting like an H minus because of pushing group, right? Because अल्यूमिनियम है, मेटल है, वो पुश कर रहे हैं इलेक्ट्रॉन्स को। यहाँ पे तो C डबल बॉन्ड हो है ना, करेक्ट?
हम्म।
क्लियर? So difficult to get that push,
हाँ सर।
right? Next, in case if you have MnO and heat, so पहले this is same as dry distillation, except that first the acid will convert into a salt form here, then you do the same reaction again. You will remove out this MnCO3 kind, understood? Just like how we have removed it earlier here. So which will convert into MnO and CO2 only. So MnO is like a catalyst that is being used, समझे? तो पहले salt बनेगा and that you will convert into this keto form, similar to dry distillation. Got it?
हाँ सर।
Next one is a decarboxylation reaction. This is the most important part of the uh, preparation part. Now notice, if you have a beta keto acid, in a beta keto acid, what is happening? This COOH has a OH group which can make a strong chelation like this, a six-membered chelation with a C double bond O. And as you heat it, it will easily break down into this form, removing out the carbon dioxide and converting into enol. Enol will convert into keto back. Hmm? Clear, beta?
यस सर।
So no matter how many number of acids you have, all of them will get oxidized. For example, if you notice in this case, with respect to this COH, it is alpha position and this is beta position and beta keto acid है. So पहले ये CO2 निकल जाएगा, उसके बाद ये निकल जाएगा. Then we can remove this one, when you can remove this one. So on total, we can remove these 4 CO2 groups. Now, even if we have beta diacids also, these are called beta diacids. In beta diacids also, the mechanism will go very similar to this one. यहाँ पर सिर्फ you instead of methyl, you have one OH group here. That's it. So same logic here. This OH and this oxygen will make a chelation. This will come out as CO2 and this part will remain as acid. So you will have this acid and CO2 remain. So because this is a beta diacid, one of the acid will go away. So this is a very standard JE question to figure out how many number of carbon dioxides you will get on decarboxylation. Clear, beta? Have you understood this point?
ये वाला थोड़ा सर मतलब ऊपर वाले चारों सी चले गए, C डबल बॉन्ड O और
नीचे वाला कैसे गया ये समझना है?
हाँ सर।
ठीक, देखो. If you have a double bond O here with O and H here like this with double bond O and OH. This is beta diacids, right? And this is the chelation which will take place within the molecule. And as you start heating here, this will break down, this will push here, and this bond will go here. Now what is happening? We'll get a double bond with OH and OH, and the other part is carbon dioxide. Now this will get tautomerized to convert into C double bond O, OH, and CH3. This is how I'm saying. So if you have beta diacid also, एक CO2 निकल जाएगा, and rest of that will convert into an aldehyde or a keto form.
सर
Got
ये
it?
समझा। सर जो
हम्म
ऊपर था, ऊपर सर
हम्म,
12 पोजीशन पे था, 2 COH।
ये वाले
हाँ, उसमें से एक एक नहीं सर, नीचे नीचे।
नीचे वाले, हाँ
हाँ सर, उसमें से एक रिएक्ट कर गया ना।
हाँ, एक निकल गया ना, और एक ही बचा हुआ है इसके लिए।
हाँ सर, पर वो फिर रिंग बनता कैसे है, इतना दूर दूर रहता है तो।
कौन सा रिंग किधर? ये वाला दूर किधर है? ये आपस में बन रहे हैं ना, ये वाला ही तो लिखा मैंने, ये लिखा, ऐसे ही तो लिखा,
अच्छा, ओके
यही
सर।
तो है। हम्म
हाँ सर, ठीक है।
हम्म क्लियर, राइट।
यस सर।
नेक्स्ट, दिस इज ऑल अबाउट decarboxylation. अगर if you have dioic acids with methyl groups in between with at least 4 or 5, okay, this should be 4 carbons in between or 5 carbons. In that case, on heating, ये डीकार्बोक्सिलेट होकर जस्ट लाइक ड्राई डिस्टिलेशन जैसे ही होगा, ड्राई डिस्टिलेशन जैसा होकर ये कीटोन में कन्वर्ट हो जाएगा। ओनली फॉर 4 and 5, ओके।
हाँ सर।
Why it is favored is because of the stable cyclic structure, that's it. Next is acid anhydride on heating. So same logic here also. When you heat acid anhydride here, so one part of the acid will go away like this. यहाँ से CO2 चला जाएगा, just like dry distillation. ये CH2 minus बनेगा, that will attach here to convert into keto form. Clear?
हाँ सर।
Usually no, nothing. Generally in decarboxylation, always, you know, this CH2 minus group will try to attack on an aldehyde or a keto position to convert into final aldehydes or ketones here, okay.
यस सर।
Next is from esters. Esters we just learned dival H, acid chlorides dival H. Next is acid chlorides can also be done via Rosenmund reduction, which is H2 using palladium barium sulfate, which is called as Lindlar's catalyst. In that, chlorine can be removed and replace that with H minus here. Further reduction is not going to happen in the presence of barium sulfate, because barium sulfate poisons the metal, palladium metal. So further ketonic groups will not be reduced. This is an alternative to dival H. Okay. So this is lithium tert butoxy. Okay. Tritert butoxy aluminum hydride. Got it? LBAH. Just like dival H, it is LBAH. This will also make acid chlorides to convert into aldehydes. If I use only 1 mole of RMGX, you can remove the chlorine, make one R minus 2 attach, so you will get this into a keto form. Okay.
यस सर।
Now, these are all the chemical preparation reactions of aldehydes. Now, notice what are the chemical reactions. In case of chemical reactions, one thing you got to take care of is that in a aldehyde or a ketone, right, you would always have two angles, alpha angle and a beta angle. Okay, clear? Now, if you notice this alpha and beta angle, alpha generally will be greater than beta. For what reason? A double bond repulsion towards a single bond would be more compared to a single bond and single bond repulsion. But that does not mean these two groups, if they are becoming bulky, will also have more repulsion. So because of it, beta increases. First thing, generally alpha is greater than beta. That is a fact you need to remember. Second thing, now if you are only comparing beta, if you are only comparing beta angles, In that case, beta angles, you notice that as the bulkiness increases or as the steric hindrance increases between these two groups, the beta angle increases. So this
Yeah.
is the order in which the angle increases. Now, usual structure C double bond O is supposed to have a pi bond here. But is this the way the uniform cloud is observed? No. This entire pi cloud would appear this way now, as if carbon does not have any electron only. In this vicinity, you will hardly find electron density. Most of the electron density will be found in oxygen side. And that shows there is a high polarity between carbon and oxygen here, with this getting negative charge and this having positive charge. Now, this is due to electronegative difference between carbon and oxygen. Okay,
Yes, sir.
right. Now, that makes as an amphiphile. Why we call it as amphiphile? Because the oxygen from here can attack onto electrophile, and nucleophile can attack on carbon, which is positive charge. So both can be done. A nucleophilic addition can be done, and electrophilic addition can be done. That's why it is amphiphile. Hmm. Second thing, if you compare the dipole moment, for example, if you take aldehydes, in aldehydes, carbon and hydrogen does not have a lot of dipole to offer as compared to that of C double bond O. Okay, but if there is a CH3 group here, CH3 group will have dipole in this direction because CH3 would have plus psi effect. So due to that plus psi effect, it is more donor, more stronger donor. So it will donate, because of which electrons will be more close towards carbon here, and that increases the polarity here. So due to that polarity, the result of these two dipole moments will only add on to C double bond O, and the dipole moment increases. So remember, generally ketones will have more dipole moment than aldehydes. And that in fact explains the fact why the boiling point of ketones in generally is greater than aldehydes of a comparable size, of a comparable molar masses. So if I have a comparable molar masses, although this is molar mass also being taken care here, but even if you have a comparable molar mass like this, I have a ketone like this with an uh, propanaldehyde like this. So in that case, this will have more boiling point. Got it? Clear, beta?
Yes, sir.
Lastly, if you have a comparable molar of various functional groups, including carboxylic acid, alcohols, ketones, aldehydes, ethers, and hydrocarbons, I forgot to write the amines here. Amines will come in between here. So in that case, what you would find is carboxylic acid will have highest boiling point because it will have strong hydrogen bonding. Then alcohols will also have good amount of hydrogen bonding. Then amines will have some amount of hydrogen bonding. Thereafter, you will get ketones, aldehydes, ethers, alkyl halides, then hydrocarbons. Okay. So this is the typical order which you will find out. Now, when you have a comparable molar mass, what is been noticed is that if you have 1, 2, 3, 4, 4 carbons here, 1, 2, 3, 4, 4 carbons here, and now you see only 3 carbons with one oxygen. Now you have 3 carbons with one oxygen. So molar mass wise, they are comparable. So what is been found is butanone is found to have a more boiling point than uh, butanol, and then propanol, and then acetone, then ethanol, and then ethers. Okay, these are physical attributes of
सर पर वो कैसा?
aldehydes and ketones. ये एक्सपेरिमेंटल है, ये जस्ट एक्सपेरिमेंटल बेसिस पे मैंने चेक करके बताया आपको दैट
ओके
इफ
सर.
यू हैव द क्लोजेस्ट वैल्यूज ऑफ वन कार्बन डिफरेंस, तो थोड़ा सा aldehyde ज्यादा रहेगा, कीटोन ज्यादा रहेगा.
यस सर.
नेक्स्ट. Next, notice what is nucleophilic addition reactions. If you have a ketone and you make an electrophilic attack from oxygen, you made an electrophile attack. So we will get this as OE plus here, and nucleophile will go and attack on this carbon. So pi bond will be pushing onto this oxygen. Therefore, you will get a complete addition reaction here. But even first electrophile getting added and then nucleophile getting added, the second step is always the slowest step. Reason being, the first step is nothing but an acid-base reaction. Oxygen has a lone pair, electrophile has an empty orbital, so quick reaction will take place. So it is an acid-base reaction, and usually acid-base reactions are strong. I mean, they are rigorous and fast. Once that happens, then the nucleophile attacking the carbon here, that means one carbon, or carbon C minus is attacking the C plus here. That will take time. So that will be the rate determining step. And overall, there is an addition. And the name of the reaction is often suggested based on the rate determining step. And in the rate determining step, there is a nucleophilic addition. Thus, these are called nucleophilic addition reactions. Now, this type of a reaction usually happens if a nucleophile is of a weaker strength. Like I have HCN, I have H2O, I have alcohol, I have ammonia, correct? Like this. Now, in such kind of cases, H plus ammonia in the presence of H plus, let's say. Okay. So in that case, what I will notice is that first oxygen will make an initiative to make an acid-base reaction. Then the remaining part as a nucleophile will attack. Next. In case if you have the first step itself is a nucleophilic addition, right? And then the lone pair of that oxygen is attacking the next one, which is electrophile present. And here the nucleophilic addition is again the rate determining step. So therefore, this is also a nucleophilic addition reaction. And oxygen attack on the electrophile is faster. Overall, the same addition has happened, but this time the nucleophile is actually stronger. For instance, I have RO minus, R minus, okay, NH2 minus. If you have like this, HC triple bond C minus, OH minus, got it, CN minus, HS minus, PHCO minus. If you have any of these kind of anions already existing, that means they are all connected with something like Na plus or K plus, or those kind of salts we have. And you know that NO plus or K plus does not have any affinity as a Lewis acid, correct? So this will be the last case what you will notice. So there might be a bond also. I mean, there might be a reaction also, or simply a positive negative attraction will happen. Okay. In case if it is RO minus and Na plus, so O minus will just attract onto Na plus as an ionic bond. No covalent bond is formed there. Got it? So what was the rate determining step? Again, a nucleophilic addition. Thus, whether you take an acid catalyzed mechanism, base catalyzed mechanism, in both the cases, the rate determining step is always the nucleophilic addition. Clear on this fact?
Yes, sir.
Now, this nucleophilic addition depends upon two factors. One is how much is the polarity on C double bond O, and what is the crowding or bulkiness around it. For example, if there is a Z group here, which is having these kind of groups, obviously the delta positive of this will be increased if there are withdrawing groups. So which are withdrawing groups here? NO2. So NO2 is more reactive than Cl, then CH3, and then OCH3. OCH3 is very strongly donating group. Got it? So that will be the rate of nucleophilic addition. Okay.
Awesome.
Now, if you have more electron withdrawing groups, more polarity. And here you notice that a pi bond is pushing electrons here, so it is helping it. Okay. So due to this help, the carbon's positive charge will decrease. And here also there is a help due to which the carbon's positive charge will decrease. And lastly, only aldehyde, uh, acetaldehyde here. So CH3 is donating, but very mild here. So if you compare the rate of nucleophilic addition, C will be the highest, then B, then A.
Yes, sir. Because of del plus.
Del plus as well as the bulkiness also. You can see this group is also sufficiently bulky. So attacking here becomes difficult. Clear?
Also.
Next. This is a rate of comparison. Usually if you have aldehydes, try to choose the least hindered aldehydes like this. And here resonance is also making it to become weaker. If you have ketones, you can check out smaller ketones, then larger ketones, and afterwards you have methyl and dimethyl ketones.
वैसे तो
Sorry,
ऊपर
phenyl and diphenyl ketones.
सर ऊपर जो था रेट ऑफ न्यूक्लियोफिलिक एडिशन आपने लिखा है सर उधर
हम्म,
बी ज्यादा बल्कि था कंपेयर टू ए
ये वाला अच्छा
हाँ
बी.
नीचे वाला बी
हाँ, in this case
मोर बल्कि देन ए राइट तो वो लास्ट को क्यों नहीं होगा
where is it? Mhm. Okay. See, benzene on giving away its pi bond, right? Remember this one. Benzene usually, if it gives away its pi bond, what happens is the ring will become anti-aromatic. So this resonance is weak, beta, which is not the case here. ये resonance stronger है. Hmm?
हम्म
So ये resonance strong होने की वजह से ये कार्बन के ऊपर पॉजिटिव चार्ज बहुत कम रहेगा.
हम्म
पोलैरिटी के रीजन है.
ओके सर ठीक है
नोटिस दिस टू केसेस अगेन हियर. चेक आउट बल्कीनेस बढ़ रहा है, रेजोनेंस बढ़ रहा है, तो रिएक्टिविटी कम हो रहा है. दिस इज अ बल्कीनेस केस हियर. टू मिथाइल ग्रुप्स, one methyl ethyl ethyl and ethyl group. Okay, this is what the data suggests us. The data suggests that देखो, if you have an aldehyde with a withdrawing group, right, and you are trying to react with cyanide, then the equilibrium constant for that is around 1420. Benzaldehyde is 210. Methoxy group is 32. And ketone is extremely low. This ketone is the least, hardly reactive. This ketone is around 38. So this aldehyde and this aldehyde is very high. So that is why it usually observes that first all the aldehydes and then the ketones will start. Okay. So even in the aldehydes, there might be resonance, but still it is an aldehyde part. The steric factor is not influenced at all. So rate of the reaction is still higher. Okay.
यस सर
Okay. Quickly go through these 6 cases. Quick. The last one I'll explain. In third one, like I said, aldehydes are always going to be more reactive than ketones. Reason being, steric factor जो है ना, इसका बहुत weak है. Correct, because of the hydrogen present here. So that will compensate its less reactivity due to resonance. And that's what the data suggests also. देखो ये सारे aldehydes are with resonance, but still they are higher than that of ketones. Correct.
यस सर
Hmm. So usually that happens. Ketones will be quite lesser than any kind of aldehydes.
सर फोर्थ वाले में भी सर वैसा क्यों रहा मतलब वो
Fourth, fourth, what happens is if you have an open chain will always have more crowding than a cyclic chain. Correct. Cyclic chain में ये restrict हो चुका है, and it is planar. It is not three-dimensionally making a difference. But here, since this carbon are not, these are sp3 and they do not supposed to be bent at one particular region, they'll be spread over the entire 3 dimension. Okay.
हम्म
So that's why cyclic are usually more reactive than acyclic. Finished.
फिफ्थ और सिक्स में भी सर फिफ्थ में तो एंगस्टीन की वजह से हो रहा है क्या वो
Fifth is for two reasons. One, we have very high delta positive here. Okay, because we hardly have any groups around methyl groups here. First, second thing, this is highly planar molecule now, isn't it? So there is no much steric factors here. So reactivity will be high here. Okay. compared to 4, compared to 6-membered ring. Got it?
Yes, sir.
Clear? And now, usually the 5-membered ring will be the least amount of it will be least reactive here. Okay. Reason being, in the case of 6-membered ring, if you notice, this is sp2. I mean, when you have sp2, it is becoming sp3 here, correct? During the reaction here. Okay. So
Yes.
when it starts to become sp3 here, that will be at a more stable form as compared to that of sp3 here, because this will have a chair form, which will make that sp3 more stable, the intermediate, because intermediate will form like this way. We have, this will be O minus, and this will be the nucleophile which is connecting, correct? So in that case, the bond angle here will be having least strain. But in the case of this one, which is supposed to be what do you say, envelope shape for 5-membered ring, O minus and nucleophile, so this sp3 will have more strain as compared to this sp3. Clear? So product wise, which one is giving more stability here? This one. So that's why it is been noticed that hexanone is more reactive than pentanone. Hmm?
सर पर वैसे रीजन से तो हम वो पहले दो थे उनको भी पीछे डाल सकते हैं ना
क्या बेटा?
सर जो
In that case, one second. Okay. Yeah. In this case, basically when you have nucleophile here, correct? Nucleophile aldehyde attacks here. First thing, the planarity is helping it a lot. While here, the other part of the molecule is not planar. ये ऐसा है. This is where the planarity is. Correct? So yet here there is a steric factors of this molecule. Got it? When the nucleophile is approaching, which is very less in 3-membered ring or a 4-membered ring, which is quite planar here. Got it? Second thing, most important thing is the bond strain here. Can you see? ये दोनों
हाँ
में कोई बॉन्ड स्ट्रेन नहीं है. ये में इस दोनों में बहुत हाई बॉन्ड स्ट्रेन है. तो would they like to be at that sp2 position, or will they try to convert into sp3 easily?
sp3
Hmm. So that's why, because of the bond strain character, these would be readily accepting the nucleophile to convert into sp3 form. Okay.
यस सर
Hmm. Now let us see the reactions applying these fundamentals. That is, the reactivity mainly is due to first nuclear polarity, second due to steric factors. When you do hydration, aldehydes पे hydration कर रहे हो in an acidic medium, let's say acidic or basic medium, let's do it with acidic medium. So what do we expect? Oxygen is expected to take H plus, water is expected to attack on carbon. Eventually you will get an OH and OH. So which means this is called a hydrate of aldehyde, or also geminal diols. Okay. In on aldehyde also, OH minus can attack here. uh, I mean, in basic medium also, aldehyde can be attacked by OH minus here. Then oxygen can take H plus from water and convert that into a hydrate form. Usually, in majority of the reactions, the reaction is mostly backward, depending upon the R group, whether this R group is more bulkier or less bulkier. But there are certain cases which is very stable. For example, formaldehyde, there are no bulky groups, so the hydrate can be stable. Acetaldehyde, that is like a exact form. 1.06 is the equilibrium constant, which means it is not very stable though, but yes, small amount of hydrate will be formed. Then ketones will hardly form any hydrate. The reaction is highly backward direction. Chlorol, fluorol, and these groups, these three are showing extremely high hydrate stability. This happens because when you take chloral and take it in, maybe let's say acidic medium, you take in it and you get a hydrate, this chlorine and hydrogen, and here chlorine and hydrogen will make a strong hydrogen bonding. Okay, clear? And because of this interaction, now this OH and OH does not tend to, you know, convert into water easily. So they can be stabilized this way. This is called hydrate of chloron. And if Chlorine can do better. Fluorine can do even better because
फिर
fluorine
वो
will
सी
have
ओ एच कैसे बन रहा है?
hmm,
फिर वो सी ओ एच कैसे बन रहा है?
by mechanism, beta. See, we have double bond O
हाँ सर,
and
हाँ
H here.
सॉरी सॉरी, अरे हाँ
Yeah.
समझा, यस सर।
Okay. Right. So that is a hydrate form here. Clear? So you got to remember in which case hydrates are stable. Apart of these cases, now notice why hydrates are stable in the other sides. Here, because of the high rings angle strain on a cyclopropene, and it is at sp2, immediately a nucleophile adding makes into two OH groups, relaxes its high strain. Got it? Therefore,
हाँ
it will like to exist more in the forward direction. So hydrate is stable. Next, this is ninhydrin. Ninhydrin on hydrolysis will immediately form these OH groups because the other oxygens can make a strong hydrogen bonding and form a 5-membered chelation. Got it?
यस सर।
Next, diphenyl propane trione. That is also the same thing. This oxygen can make, you know, OH and OH here, which can be connected with these oxygens this way. Okay.
हाँ
So
सर।
these are three important examples wherein, other than the given ones, wherein you will see the percentage diol formation is more stable. Okay. Next is reaction with alcohols. Instead of water, now I am taking alcohol. You cannot make alcohol to directly add on to acids. That's why you take dry HCl. On taking dry HCl, the oxygen first engages with H plus and allows the carbon to get high positive charge by which alcohol can attack. And that converts into this compound, okay, which is hemiacetal. Hemiacetal is still reversible with this reaction, which means this can easily break down. You could notice that there is a Cl minus, you know, within that solution, which can again take away H plus, pushes this, remove this part, RO minus, okay, and again that will take H plus and converts back into R dash OH. So this is highly backward reaction. In fact, hemiacetals are unstable in both basic medium and acidic medium. But if you push excess amount of alcohol, the reaction can be seen moving slowly into the forward direction. Okay. So for these reactions, that's why alcohol composition taken is in excess. Okay. So now, if this alcohol, if once you have this hemiacetal, and if you have excess of alcohol, this hemiacetal will further react, right? See, how does it react now? First, this is a hemiacetal form, okay? And this hemiacetal can take again H plus from the, dry HCl here, convert into OH2. OH2 is a good leaving group. So this lone pair will try to push the electrons and leave the H2O group out of it, by which you will get this as C double bond O R group here. And the second mole of alcohol will attack, which will make it to become OR dash here. So what is eventually remaining? We have OR dash and OR dash, which we call it as acetal. Okay. So first we get hemiacetal, then we will get acetal. Clear?
यस सर।
Right. So you can see this now. Ketones does not form acetals with simple alcohols, but they react with 1,2 diol groups to form cyclic acetals. Okay. Because if you take ketones, right, like this, there is a ketone, 2 moles of alcohol, and you are trying to get this form here. It is highly in the backward direction, beta, even if you take excess amount of alcohol. Okay. And one of the reasons why it is happening, is the entropy factor. Because, see, what is that you are doing? You are trying to make one OR bond in the expense of breaking a pi bond here, correct? So it is like you are making one sigma bond and breaking one pi bond here. But this pi bond and this OH bond you have to break, correct? And this OH bond and this CO bond and OH bond, you are trying to compensate that with a sigma bond of CO, new CO. Now what happens in that case, the delta H value is hardly changing. बहुत ज़्यादा energy difference नहीं आ रहा. It's not like you are making a very strong bond or you're trying to make a very weak bond. So it is not neither completely exothermic nor endothermic, which means this reaction is highly entropy driven. And you know that delta G is equal to delta H minus T delta S. So if this factor is not much contributing, the reaction is highly entropy driven. Now notice the entropy here, beta. On the reactant side, we have 3 molecules. Product side, we have only 2 molecules. Correct?
Hmm.
So entropy is decreasing, isn't it?
Yes.
That means this is becoming positive. So is this a feasible reaction? No. So reaction would always lie on which direction? Backward. Okay.
Hmm.
So that is why hemiacetal, acetal formation in all the cases, whether you take aldehydes or ketones, it is not a very lucrative reaction. Got it? It would be mostly driving in the backward direction. Aldehydes, in some cases, it is still feasible to give some amount of acetal form which can be extracted out. That means you can slowly 0.5 percentage, 1 percentage, if it is forming, you can extract it out by various methods, maybe distillation, right? Using those methods, you can extract it out. But by ketones, it becomes very difficult. But what is an alternative path? Instead of taking 2 moles of alcohols now to account for that entropy factor, imagine I took a glycol. Glycol is only 1 mole, right? It is only 1 mole now. So I have 1
हाँ
mole and 1 mole converting into 1 mole and 1 mole. So entropy factor is also almost zero, correct? So if you
yes.
compare this reaction versus this reaction is at least favorable in the forward direction to some extent, correct?
हाँ सर.
So that's why if you want to get ketones to convert into an acetal form, you better take a diol forms here. Instead of taking a 2 different alcohols, you take diol alcohols. So that first it helps in chelation, and you know that chelations usually make it more stable because the entropy factor decreases to a larger extent. Hmm? Because
हाँ.
straight chain और cyclic chain में entropy काफी कम होता है. So entropy वैसे भी कम हो रहा है, right? So therefore the reaction will drive in the forward direction. Okay. And if you make this, ketones also into cyclic, we know that compared to straight chains ketones, cyclic ketones are more reactive. So this will be more reactive and the reaction would happen even better. Hmm?
हाँ सर.
Clear, beta?
Yes.
Now, although this is a ketone, and if you take 2 moles of alcohols, it is still going to form an acetal because at least one factor is taken care of. Hmm?
हाँ सर.
Right. Next. If you notice the intramolecular acetal formation, that is within the molecule, I have 2 moles of alcohols here. So one will attack from here, the other one will attack from here. You will get this cyclic form. Now you have only noticed one molecule making 2 molecules here. So entropy is actually increasing here. So this is highly spontaneous. Hmm?
हाँ सर.
Got it? Even this formation is also spontaneous. Got it? Clear, beta?
Hmm.
Now, this is used as a very important application when you want to do a selective reduction. For example, I'm trying to reduce this ester, I'm trying to reduce this ester, keeping the aldehyde or a keto form intact. We do not want to disturb that. So what do? We would be using lithium aluminum hydride in this case. Hmm?
Hmm.
So I could, uh, if I use lithium aluminum hydride directly, it can reduce the ester form also and keto form also. And this is what is the product you will get. But what if I do not want to reduce this ketone? So what you do? You use glycol first with dry
Hmm.
H plus. So this glycol in dry H plus will make this keto form into acetal form. Correct?
सर वो कीटो पे अटैक करता है एस्टर पे नहीं करता क्योंकि डाइप्रेस ज्यादा है कीटो पे.
Yes, beta. Yes, del plus बहुत ज़्यादा है. That's why carboxylic acids will have a very different set of reactions. वो aldehydes ketones जैसे react नहीं कर पाएंगे. Okay?
हाँ सर.
So that will make a acetal form here, and thereafter lithium aluminum hydride will reduce this part. reduce हो गया. And you know that acetals are unstable in acidic medium, so immediately फिर से acidic water डाल दो, आपको वापस कीटोन आ जाएगा. हम्म.
So it acts as a protecting group.
हम्म.
So it
Protective
acts
group,
like a
correct.
protecting.
It is acting. It is acting like a protective group. Okay.
Hmm.
See the next example. Same logic. This is acid chloride. CH3 MgBr will make 1 mole to add here, right? So I want this. I mean, if at all you open it with excess, you'll get addition on all the positions. But if I want to make sure this aldehyde part is been, restored or remain the same, so
तो
what I
इधर
can do?
तो सर इधर तो डबल बॉन्ड सीएल पे अटैक होना चाहिए ना, क्योंकि सीएल माइनस आई की वजह से, स्ट्रॉन्ग माइनस आई की वजह से वो डेल प्लस बढ़ा रही है.
नहीं बेटा, फिर भी आप एसिड क्लोराइड एंड aldehyde को कंपेयर करोगे. If you have a double bond O, Cl here, right? And compared to that of keto part here, right? ऐसे कह रहे हो, right? Clear?
हाँ.
Now what happens is chlorine is a good leaving group. तो एडिशन रिएक्शन होगा ही नहीं इस पे. आप लेट्स से अज्यूम करो यहाँ पर आप कीटो ग्रुप भी लेकर आने की कोशिश करो, मतलब हेमिएसिटाल लेके आने की कोशिश करो इस तरीके से, करेक्ट. राइट.
हाँ.
ये ना ये पुश करके इजीली निकाल देगा सीएल को. सीएल इज अ वेरी गुड लिविंग ग्रुप, करेक्ट. तो
हम्म.
ये एसिटाल कभी स्टेबल हो ही नहीं पाएगा इसके ऊपर. ऑलराइट. या
अच्छा.
तो इसका रिएक्टिविटी कम होगा बिकॉज ऑफ ए डोनेटिंग ग्रुप लाइक OH या OR, एस्टर्स, एसिड्स एंड सो. अदरवाइज इन द केस ऑफ क्लोरीन, क्योंकि क्लोरीन एक अच्छा लीविंग ग्रुप है, वहां पे एसिटाल या एसिटाल बनने ही नहीं देगा. ओके.
सर तो वैसे जो होता है अटैच वो, जैसे साइक्लिक स्ट्रक्चर में, वैसे बस कीटो पे ही बनता है और किधर नहीं.
Keto and aldehydes and ketones only. And within aldehydes and ketones, if you are very particular about one equivalent, then aldehydes first, because aldehydes are more reactive than ketones.
ओके सर.
Hmm. Done.
हाँ
So
सर.
you notice that CH3 MgBr excess, we convert this into an alcoholic part. Well, it is not converted into alcohol immediately. Water आने के बाद आएगा. यहाँ पे I'll just change this part as O minus. First you'll get this as O minus here, and thereafter when you hydrolyze this will become OH and this part will become ketone. So this is how the product will be. Okay.
यस सर. सर वो H2O डालने के बाद सर वो उड़ जाता है प्रोटेक्टिंग ग्रुप, सर वो कैसे होता है?
Yes बेटा, हेमीएसिटाल या एसिटाल दोनों ही अनस्टेबल है ना एसिड में.
राइट
ये
राइट.
हमने ईथर्स में पढ़ा है, ईथर हाइड्रोलिसिस.
इधर तक पहुंचे ही नहीं थे.
अच्छा. ओके. हाँ, ईथर में हमने मतलब ये पूरे हाइड्रोलिसिस कैसे होते हैं पढ़ाए थे वहां पर. ओके.
अच्छा.
लेट मी
ओके.
लेट मी शो यू हियर. ओके. एक मैं एग्जांपल में आई पुट इट एज अ नोट. ठीक है. बस वो एक ही पॉइंट चाहिए ना आपको, तो यहीं पे लर्न कर लेते. सपोज आई हैव, लेट्स से, and OR group. ठीक है बेटा.
हम्म.
And you taken in an acidic medium. So what would happen? You'll get this as OH R with plus charge and OR, correct?
यस.
Acidic medium hai. So protonation is bound to happen. So the lone pair on this will push so that this OR can go away.
हम्म.
So what do we get? We'll get this as double bond OR plus, and one alcohol will come out. Done. Clear? Then,
यस.
because it is in an aqueous solution, water as a nucleophile will attack, and that again converts into OH and OH here. OH2 plus hoga, because it is in an acidic medium. You will notice this as OR and OH, which is hemiacetal. You know,
हाँ.
this is hemiacetal. And since it is still present in an acidic medium, right? So lone pair will be taken by this H plus. You will get this positive value, and you'll get this as OH. Now again the lone pair from here will push, alcohol will go away, and you will have this as double bond OH plus plus ROH. Okay. And
हम्म.
this would give away H plus to convert finally into keto form, right? So this is how the hydrolysis will take place. Got it?
Yes, sir.
Acetals are stable in basic medium because basic medium में ketones ethers को कुछ नहीं हो सकता है, right?
Hmm.
Because ether themselves will carry lone pair, but hemiacetal will not remain stable. ऐसा क्यों? Because you have OH here, OR here. OH minus can take away this H plus, right? So by which you'll notice that O minus will be there and OR will be there. So this will push and remove this OR to convert back into ketones. So which means hemiacetal is unstable in both acidic and basic medium, but acetal is stable in basic medium but unstable in acidic medium. Got it?
Yes, sir.
Right. What is this? If you have alcohol, thioalcohol, glycol, thioglycol, correct? Now this is a thioglycol which I'm using to react with aldehydes. So you will get this thioacetal form. Now, what is the reactivity of thioacetal? First, if thioacetal is being treated with something like a strong base like Br minus Li plus, so butyl can take this H plus away, gets a negative charge. Why this negative charge is stable in the case of sulfur and not with oxygen? Because sulfur has an empty d orbital, it can make a resonance, d orbital resonance. Okay, so this is
Yes.
a stable intermediate. Now, once you get this intermediate, we can use it for multiple sources. For example, if I react with alkyl halide, so this can attack R, remove this X. So you get an R substitution. So देखो we started off aldehyde, अभी हम लोग ketone की तरफ जा रहे हैं. Yeah, I can use D2O. That means I can replace this hydrogen with deuterium. I can get a D here.
Hmm.
And now if at all I use this with, HgCl2 in water or CdCl2, anything, cadmium chloride or HgCl2, then Hg will take away all the sulfurs here, convert into HgS precipitate, and this part will get hydrolyzed and convert into OH and OH, which is unstable, to convert into keto form. Okay. Now
Huh.
instead I use H2 by nickel or Ranne nickel. If I use Ranne nickel, then this Ranne nickel will provide hydrogens here and remove sulfurs from this end. So you will get this part separated and this part will convert into alkane. Got it? And in the
Yes.
presence of nickel and hydrogen, ये दोनों सल्फर्स निकल के साथ black precipitate बना देंगे and this will convert into an alkane. Got it?
Huh.
In the presence of D2O, this O minus will take D plus and thereafter with HgCl2 again, HgS will become a precipitate and this will become a keto aldehyde part. Okay?
Huh, sir.
So this reduction part to convert into aldehydes and ketones into alkanes is called Mozingo's reduction. Clear how the
Yes.
glycols are making reactions? Hmm?
Huh, sir.
When you react with HCN, HCN is a weak acid, so you will hardly have any H plus available or Cn minus for that matter. So what you do, you will add some amount of KCN to it so that you can make a nucleophilic rich part here. Okay. So on adding KCN, first Cn minus will initiate the reaction. So it will go and attack on the carbon. O minus will come and O minus will take the H plus from HCN. Okay. And that's how you can get this as cyanohydrin. On the same location, we have OH and cyanide. So it is called cyanohydrin. Okay. Cyanohydrin is also reversible reaction because you kept in an acidic medium, just like acetal jaisa hai ye. Okay. It is like an acetal form. So it can take H plus, becomes OH2 here, right? So that will push that cyanide group out by taking out this H plus. यहीं से H plus ये ले लेगा carbon and convert into HCl and come out, and this will become a double bond again. Hmm. Now remember, reaction takes place with all the aldehydes and ketones usually. That is, this aldehyde, these ketones, everything, correct? But if you have a methyl ketone with a phenyl group or a diphenyl ketone or an extremely bulky ketone, in such case you will have no reaction. In this case, no reaction. जेई मेंस में इसको कंसिडर किया गया है, सो प्लीज रिमेंबर, ये इंपॉर्टेंट है, ये हमेशा कंफ्यूज होता है. गॉट इट? This one is always a confusion. Should we take it or not? Okay, it has been taken. that ये reaction देता है. Okay, ये typical integer type question है, यश. So you can notice. So which of them will give products? 1, 2, 3, 4, 5, 6. Which will not give products is these two. Just any doubt here?
No, sir.
Next. If you have an aldehyde, you react with HCN, right? You'll get a cyanohydrin. That on hydrolysis, further hydrolysis, can make this cyanide to convert into COOH. Okay. So thereby you will get alpha hydroxy acid, which you call it as lactic acid. Suppose if you have an alpha beta unsaturated aldehydes or a ketones, and then you're reacting with HCN. Okay. I can get two types of reaction here. That CN minus can actually attach here, pi bond can move, O minus can form. So that will lead to formation of something called 1,4 addition. Or directly cyanide can get added here, oxygen can take H plus, and you can get 1,2 addition. 1,4 addition, because this is an enol, which will again convert into ketone, you will get this as 1,4 addition. Usually, if the temperature is kept very low, that means below 0 degrees, then 1,2 addition is more favorable in these cases, which is called as kinetic product. Okay. And if you keep it at normal temperature, that is 25 degrees and above, you'll always see 1,4 addition is more favorable. So this product will form, and this can be further again, once if you react with one more mole, it will convert into this product. Yes, clear on that?
हाँ सर. सर 1,4 को और एक मोल ऐड करके 1,2 कैसे बन गया?
अभी ये बन चुका है ना, अभी फिर से अल्डिहाइड आ चुका है. अब और एक मोल डाल दो तो क्या हो जाएगा, इस बार ये रिड्यूस हो जाएगा. 1,4 मतलब ये
दो
प्रोडक्ट
सेकेंड.
की तरफ, मतलब सेम प्रोडक्ट नहीं बेटा, मतलब इस तरफ जा सकते हो ऐसे हमसे.
अच्छा, हाँ, ओके. यस
I'm
सर.
not saying same product. Okay.
हाँ.
Right. So I'll just put it here. This is KFP, kinetically favored product. This is TFP. At this point, I do not expect to go into further details about why KFP and why TFP. We will see it when we prepare it for advance after mains. अभी के लिए जरूरत नहीं है. Okay.
सर वो बीच में क्या कार्बोटाइन या ऐसा इंटरमीडिएट स्टेबल हो रहा है क्या?
कार्बोकेटन नहीं बन रहा है कहीं पे भी.
हाँ सर, सॉरी, कार्बोटाइन गलती से बोला सर. इंटरमीडिएट कोई.
हाँ, इंटरमीडिएट बेसिकली यहाँ पर डेल्टा पॉजिटिव इसका ज्यादा होता है कंपेयर टू इसका डेल्टा पॉजिटिव. इसका लूमो ऑर्बिटॉल जो होता है ये वाला, ओके, ये ज्यादा एक्सपोज्ड होता है एज ए सॉफ्ट एसिड. गॉट इट.
हाँ.
एंड CN माइनस जो है वो सॉफ्ट बेस की तरह अटैच करता है इन द केस ऑफ थर्मोडाइनमिक प्रोडक्ट. ओके. सो ये फंडामेंटल है. सो अभी के लिए जरूरत नहीं है. ओके.
यस सर.
Now, if you want to get a strictly 1,2 addition product only, then you take a little bulky cyanide here, trimethyl silicon cyanide, and then water. So, by which you can only get 1,2 addition instead of HCN. Got it? Because 1,2 addition पे carbon का positive charge ज़्यादा है. So, that can be helped by this cyanide. Next, reaction with NHSO3. Okay. See, NHSO3 has a sulfur with a lone pair here, which will be acting like a nucleophile. So that sulfur's lone pair is the one which will attack on the carbon here, right? As it attacks, you will get O minus, and this oxygen already has a O minus and Na plus part here. So there are two O minus groups which will remain here. And on hydrolysis, this O minus will take H plus, and you will expect a salt kind of a form. That's why it will be a white precipitate here. Clear?
यस सर.
Now this is also reversible. That means if you use it in acidic medium here, again, sorry, basic medium here, the reaction will go backward direction and again you will get an aldehyde form. Okay. Now this is very interesting to notice that all the aldehydes will give positive sodium bisulfate test. It's a very important test to determine the presence of aldehydes and ketones. Okay. And only methyl ketones will give you positive bicarbonate test. Correct? Matlab,
Hmm.
usually the ketones which you are reacting, because this is a very bulky nucleophile, if it goes to a bulky ketone, there is no reaction. But if it has at least one side methyl group, still the reactivity is observed, precipitate is forming. Which means groups which does not give sodium bisulfate test. This one, देखो दोनों तरफ ethyl है, so no reaction. Propyl ethyl, no reaction. Phenyl, now this is an exception. Phenyl is there, even then the methyl is there, still the reactivity does not take place. Phenyl ethyl, no reaction. Phenyl isopropyl, tartabutyl methyl, no reaction. Phenyl phenyl, no reaction. So these are the ones which will not give any test with NHSO3. Rest every aldehyde will give. Normal ketones will give, like acetone, okay, butanone. Those kind of cases will be given. Clear?
हाँ सर.
Now you can see when you hydrolyze this one, again you will get this as an aldehyde, and this will get back into the sulfate form. Okay. Now used for purification or separation of aldehydes and alcohols. How is it used? Imagine I have an aldehyde and alcohol mixed. I treat with NHSO3, and this will form precipitate first. Alcohols will be filtrated out. And once you get precipitate, again you heat it in the presence of acidic medium, you will get an aldehyde dissolved. Got it?
हाँ.
Next reaction is with ammonia derivatives. Ammonia derivatives, as in we have NH2 with Z. What is this Z? Z is any group. It could be varying from hydrogen to alkyl group or any group. But the requirement is we should have NH2 here. Okay. In that case, this H2 and oxygen will be dehydrated or condensed to form C double bond N bond. And usually these compounds are crystalline solids. Okay. And NH2Z is a very important test used for the presence of carbonyl bonds, whether there is an aldehyde or ketone present or not. Okay. While removing out this water, you will be able to see two kinds of products will be formed, and both of them are geometrical isomers, anti and syn. If it is the aldehyde which you are taking, and then you are making this kind of compound here, right? Yeah. So then we will get anti and syn form. Now notice this is an aldehyde, and I'm using hydroxyl amine. Instead of this Z group, I have OH. Then the product what you'll get is C double bond N and OH. This functional group is called oxime. And in the case of oxime, you will get syn and anti. So in case if I get like this, C double bond N with OH and H and R. If and lone pair here. If H and OH are on the same side, we call it as syn aldoxime. And if H and OH are on the opposite side, then we call it as, sorry, anti aldoxime. Okay. You will check out the priority on the basis of H and OH. Got it?
Yes sir.
And aldoximes are also colored. So if you get a colored crystal as you cool down, that means you must have a presence of aldehyde or a ketone.
तो कौन
Got
से
it?
कलर का?
Hmm?
ऑक्साइड कौन से कलर का?
कोई भी कलर हो सकता है, वो डिपेंड करता है आर पे ना बेटा.
हाँ सर, पर यूजुअली
एक
मतलब.
पर्टिकुलर कलर नहीं होगा.
अच्छा ठीक है.
रेंज ऑफ कलर्स है ये सारे. ओके. पर्पल टू वॉयलेट. ओके. सॉरी, रेड टू वॉयलेट. Check. If you have an aldehyde and you treat with hydrazine, so same logic. यहाँ से ये H2 and O will be removed out. You will get this as N. Now, whenever you have ine group, right, or zyne group, zyne will convert into zone. The name remains the same. It is called as, it is coming from aldehyde, so it is called aldehydrazone or aldhydrazone. Clear?
हाँ सर.
Similarly, if you have instead of NH2 have NHPH, so this is called phenylhydrazine. So phenylhydrazine will now become phenylhydrazone. Okay. And now, if you have NHC double bond or NH2, this is called semi-carbazide. Okay. So this azide will become azone. So this is semi-carbazide and this will become semi-carbazone. And this is the most important one. This is 2,4-DNP, that is dinitrophenyl hydrazine. And this oxygen and H2 will be removed out. You will get this product. This will have different shiny crystal forms. And this is main test used for identifying aldehydes and ketones, known as 2,4-DNP test.
हाँ
Okay.
सर.
And the reagent is called as Brady's reagent. This is called Brady's reagent. Clear? If you have NH2R, then it becomes imines. Correct? And if this R dash is actually a phenyl group, we call it as Schiff base. It is called Schiff base. And if you have diamine, now here is an interesting fact. If you have a diamine, that means instead of H2 nahi hai yahan par, and you have only one H, correct? Then also you can remove out this oxygen by simply making this into an enol form. So what you can see, you can get CH, double bond, CH and OH. ये enol form है. And then you have HN with R dash and R dash, correct? So remove out water in this form. Clear? So as you remove the water in this particular way, correct? So then what do we get? We will get an amine with a ene. So that's why it is called enamine. The product is called enamine. So if you take secondary amine, what is the product you will get is enamine. Clear?
हाँ सर. सर पर वो H2 निकालने की जगह सर डायरेक्टली ऐसा मैकेनिज्म एक बार बोल सकते हो क्या?
हाँ, नीचे पूरी मैकेनिज्म से भी सारे, पहले सारे रिएक्शन पढ़ा है आपको. ओके.
यस सर, ठीक है.
अब ये यहाँ से पूरे रिएक्शन मैकेनिज्म से कैसे हो रहा है. ओके.
हाँ सर.
सी फर्स्ट जेनेरिक मैकेनिज्म पढ़ते हैं कैसे हो रहा है. First proton, because you are maintaining at a very mild acidic condition around 4 to 6, so lone pair will take H plus first. Then the lone pair present on nitrogen will attack as a nucleophile. So this is a rate determining step, correct? And it will get a nitrogen form here. And since nitrogen has a positive charge, the lone pair from oxygen will take this H plus internally. This is called intramolecular proton transfer, and by which you will get OH2 plus. And nitrogen's lone pair will push it so that OH2 as a good leaving group will leave out of the molecule, and you will get this form. And from here, H plus will be shredded off, converting into an C double bond N form. Done. This is the same mechanism with all of them. Clear? 2 डिग्री का नहीं, मैं सारे 1 डिग्री का कह रहा हूं. Okay, 1 degree amines का. Now in this case, you can notice that there is a formation of this sp2 from sp2 carbon. There is an intermediate formation of sp3 carbon. When such type of reactions happen, you call it as tetrahedral intermediate formation or SNTD reactions. Okay. In the overall reaction, what is happening? We are seeing an addition happening and then an elimination happening. That's why they are also called SNAE mechanisms.
हाँ सर.
Right. Next. Suppose if you have two aldehydes back to back like this, sorry, from here, let's say, if you have one aldehyde here, you got this one. If at all I took 2 moles of this aldehyde, right, this side also the reaction can take place and you will get this one. This is called dihydrazone. Okay. And instead of 2 moles, if at all I have 1 mole but 2 aldehydes, this is phthalaldehyde. Okay. In phthalaldehyde, if you make NH2 reaction, one, this oxygen and H2 will go away, and this oxygen and H2 will go away, and we will get a double bond and double bond here. So this is the product you will get. Okay.
Yes sir.
Right. Next. 2,4-DNP is also called as Brady's reagent. This is used for carbonyl compounds. It can have anywhere from yellow, orange, and red color crystals forming. Okay. If you have only ammonia, you will get imines. Imines are unstable in water. They can immediately break down and convert into aldehydes again. Okay. But if you push excess amount of ammonia and aldehyde, the reaction will go in the forward direction. And especially if you have a formaldehyde with ammonia with at least 6:4 ratio here, then it will form a compound called erythropine. This is called erythropine. Its actual name is hexamethylene tetraamine.
रियल नहीं
Okay.
समझा.
हाँ हाँ.
रियल नहीं समझा.
देखो पहले ये बनना चाहिए आपको, बराबर. वाटर निकल गया, यहाँ से O निकल गया, यहाँ से H2 निकल गया, तो ये बनना चाहिए ना इमाइन.
हाँ.
यहाँ पे H2 है, सॉरी CH2 है. करेक्ट. क्लियर. अब ये CH2 इमेजिन करो, ये सारे एक दूसरे को कनेक्ट होते जा रहे हैं. ओके. 4
हम्म.
मॉलिक्यूल्स ऑफ अमोनिया है यहाँ पर और 6 मॉलिक्यूल्स ऑफ aldehyde है. तो कैसे कनेक्ट होंगे? CH2 डबल बॉन्ड NH. नेक्स्ट मॉलिक्यूल है यहाँ पर, लेट्स से CH2 डबल बॉन्ड NH. सो कैन यू सी दैट ये लोन पेयर यहाँ पर अटैक करेगा, तो ये पाई बॉन्ड दूसरे पे अटैक करेगा ऐसे. हम्म,
हम्म.
है कि नहीं?
यस.
ओके. अब ये बन जाएगा, तो ऐसा बनते बनते कैन यू नोटिस दैट देर आर 4, अगर 4 लोगे तो 4 नाइट्रोजन के पास 4 हाइड्रोजन होंगे.
हम्म.
एंड दोज 4 हाइड्रोजन इन द कीटो फॉर्म हियर. मतलब ये इसको ऐसे समझो कि हमने ऐसे लिख दिया, ये C डबल बॉन्ड O और H है, और एक HCH डबल बॉन्ड O है. सो 2 नाइट्रोजन के हाइड्रोजन्स और एक ऑक्सीजन, ये दोनों निकल गए, और दूसरे मॉलिक्यूल के 2 हाइड्रोजन्स और ये ऑक्सीजन दोनों निकल गए. करेक्ट.
हाँ सर.
एंड दैट गॉट अ कनेक्शन. ये यहां से नाइट्रोजन नाइट्रोजन कनेक्शन हो गया, यहां से भी नाइट्रोजन नाइट्रोजन का कनेक्शन हो गया, दोनों तरफ से. ओके.
हम्म.
सो दैट्स हाउ यू विल एंड अप गेटिंग ए यूरेट्रोपाइन, a cyclic
सर,
structure like this. Hmm?
सर और कितना बाकी है अपना ये वाला?
तो रिएक्शन चलते रहेंगे. दिस इज द लास्ट वन विच इज व्हाट यू से, द रिएक्शन सेट में से ये लास्ट वन है. उसके बाद टाइप्स डिफरेंट हो जाएंगे.
अच्छा.
aldol, canizero, that's a different type now.
हाँ सर.
Right. So you can see that secondary amine liya to enamine aaya. That's what we discussed. So this is, if notice this one, I have a ketone with a secondary amine, you get a enamine. Correct.
हाँ.
What is the importance in enamine is the lone pair is always in resonance with a pi bond. Correct.
हम्म.
Because of which this carbon holds delta negative charge. So if you react with an alkyl halide, this R minus will attack here, removing this X via SN2 mechanism, and you will get this product. And then on hydrolysis, this bond will break and you'll get back to the ketones. So, matlab, if you want an alpha substituted alkyl group, this is a better method to do it. Correct.
हाँ
On
सर.
this alpha position, I want to substitute some alkyl group. So, this is a better method to adapt, and this is called Stokes enamine reaction. Hmm?
यस
Yes,
सर.
clear, beta? Done.
हाँ सर.
Okay. So, right, beta. So, we'll stop it here.
यस सर.